Okay, this is the main content of this chapter. We are going to use the GMM for the instrumental variable regression model, and everything is standard, right? So there's nothing much I'd like to say. Just we may use simplified x, z, and beta. So it's exactly same as what we learned in chapter 2. So first, let's define the moment function gi. Gi beta will be defined in this way. Okay, because if you imagine the exogeneity assumption, we are using this moment restriction. This is assumption based on moments expectations. So we are going to use this, and if you plug in beta 0, then this part will become u. So if beta equals to beta 0, we get expectation of gi beta 0 is expectation of zi yi minus xi transpose beta, and that is beta 0, that is expectation zi ui, which is 0 by exogeneity assumption. Okay, and also we learned it's unique if rank of expectation zi xi transpose is k, right? We learned this identification in chapter 2. Okay, now from now on, it's just mechanical algebra. Part B. Let's differentiate this guy. It's easy. This is zi xi transpose. By the way, let's think about the dimension. It is m by 1, and this is 1 by 1, right? Because it is 1 by k and k by 1, right? Now, if you differentiate, so g is m by 1 function, and then you have to differentiate this way, right? So g is m by 1 function, and you are going to differentiate that using a vector 1 by k. So beta should be transposed. It is m by 1 is 1 by k, so this is m by k matrix as a whole. Okay, that's pretty simple. So if you define g, capital G, as expectation of the derivative, it does not depend on beta, but if you just use the notation, then it is minus expectation zi xi transpose. Later, the minus sign will go away, right? So it doesn't matter. And show that its rank is k. Rank of G is k by the IV regression assumption, model assumption. Okay, right? Because we already assumed that for identification, so we have to have that here again. And part C, we are going to think about omega, that is defined as gi beta 0 and gi beta 0 transpose. Okay, so gi beta 0 is zi ui, and the second part is zi ui transpose, right? You must be familiar with this simple plugin. And then we are going to write it as ui squared times zi transpose. There is nothing more we can do in general. So, but often cases later we may use if homoscedasticity is assumed, that means ui squared, the variance of u given z, is always fixed as sigma squared almost surely. Okay, for any, almost surely means for any z. Okay, if you have this, then you may simplify this as like this. Okay, so this is another interesting problem. So we will think about it later. And this is C, and part D is super simple because so supremum of over beta of this is pretty simple. It is just supremum over beta, because this guy does not depend on beta. It is constant for beta, constant with respect to beta. So supremum does not do anything. It's just constant. Okay, so if you take expectation of that, then it is expectation of ZIXI transpose, right? So if you assume that it is finite, that's sufficient. So pretty simple in this case. And part E, so find the optimal weighting matrix. So optimal weighting matrix is known as omega inverse. And earlier we learned omega was expectation of ui squared zi transpose. So I will think about two different cases if heteroscedastic. Heteroscedastic, like, then we need to, so basically if you can estimate, if you can estimate omega using finite sample, right, then I will use its inverse. This is what we are going to do. Then how can we estimate omega? Let's think about it. So first, we know the expectation can be replaced by this. That is pretty straightforward. The problem is here, z is observed. So instrumental variable, you can use just the data, but this is unobserved, right? So we have a problem. So we need to use two-step method. So in the first step, use identity matrix. So identity matrix, m by m identity matrix. This is identity matrix, and then obtain a preliminary estimator theta hat. So using a random kind of ad hoc weighting matrix, still you can minimize the GMM problem, and you are going to obtain a preliminary estimator theta tilde. This is consistent. It is still consistent, right? We learned it is consistent, but it may be inefficient. So then what we are going to do here is then calculate ui tilde as this. So use a preliminary estimator and plug that into here. So calculate the residual. And then using this residual, I am going to calculate the sample variance. It is the sample variance of u tilde squared and zi transpose. So now you can calculate everything. You can calculate, of course, you can calculate zz prime, and also you can calculate the residual from here, and then you just take their average. And then from here, w hat will be its inverse. Okay, so this is the first step, and then second step is using this as weight, and recalculate the minimization, and then you are going to obtain the efficient estimator. Okay, that is heteroscedastic case. Now, as a side note, I will think about homoscedastic case where expectation of ui squared given zi is sigma squared. In this case, remember, omega was expectation ui squared zi transpose. It is simplified to sigma squared times expectation zi transpose. Okay, right? Then how can, like, we need its estimator. So expectation can be replaced by the sample average. And then the main problem is here. sigma squared, you may think that we can use the same idea, right? Like in the previous part, we may use something like this. Okay, so we learned a preliminary residual may be used to replace the true residual. But here, that is fine. This is not wrong. This is okay. Two-step method is okay. But what I recommend is a clever way. Way is, so you are going, so think about this. Expectation of Zi transpose is, so ignore the sigma squared. It is proportional to omega. Okay? And that means, and define W tilde as its inverse, which is proportional to omega inverse. Okay? So the main difference here is, say, optimal weighting matrix is omega inverse, but instead of the omega inverse itself, I'm going to consider another weight matrix which is just proportional. Okay? Then the difference is, their difference is sigma squared, or 1 over sigma squared. Okay? Then the point here is multiplying 1 over sigma squared does not change the minimization problem, right? So for example, if you minimize x squared, or if you minimize 100 times x squared, or if you minimize like x squared over 100, they are same thing. Always minimum is the same thing, right? So in your calculation, this sigma squared multiply positive constant does not matter. So that is the better way. And then when you just need this part, you don't need preliminary estimator, because you may estimate, I will use this directly. Okay, so you can just use this much without thinking about sigma squared, because that does not matter in minimization. So you can just do it in one step. If so, remember, it is when your error term is homoscedastic. Okay. All right. So then next, this was part E and part F. Let's think about the part F. Optimal weighting matrix. Now you are going to verify all the sufficient conditions for the asymptotic normality. Right? Actually, we already did. So you don't need to worry about the details. Like, you just check the lemma, check the conditions for the lemma, and then you are going to have G transpose omega inverse G and total inverse. This is the final result. And then, right, we did everything. So first, so let's check the assumptions. First, unique solution. We did that. Second, theta is compact. It is implied by this assumption. And 3, continuous, obvious, because the derivative is Zi xi transpose. So it is constant, so it is continuous. And number 4, we already did in part D. And number 5, W hat converges in probability to W, and this is non-singular. So that is by the assumption, right? Like Z, Zi, Z prime should be non-singular, right? And number 6, G is rank K. We proved it. Rank of G is K. We proved it. And number 7, omega, we already derived it. So all the assumptions are satisfied. If you verify all of them, then you can just calculate this, right? So think about that. G was minus expectation Zi xi transpose, and omega was expectation ui squared Zi transpose. All right. And then G transpose omega inverse G is expectation xi zi transpose expectation ui squared zi transpose inverse times expectation zi xi transpose. So minus will be cancelled out here and here. So, and variance is its inverse. We are taking the inverse, right? So this is your asymptotic variance. And if you have homoscedasticity, it simplifies a little, like, I'm sorry, if it is sigma squared, then you may simplify this to, so sigma squared times expectation xzi transpose, expectation zi transpose inverse, expectation zi xi transpose, and total inverse. Okay, this is the asymptotic variance simplified case with homoscedasticity. Okay, now then, this was part F. Now, the last question, part G. How can we estimate that, right? So we are going to estimate ZI transpose using their counterpart, simple. And then the problem is ui squared zi transpose. So when you calculate the variance, you already have, right? So u will be replaced by u had that is defined as yi minus xi transpose beta hat n, right? After you estimate beta hat, we are calculating the variance, so you may use beta hat. So then the whole thing will be replaced by hat squared times zi transpose. And then, and if homoscedastic, then you can estimate the beta sigma squared using this guy. So that is also possible. So, and then in the end, think about this. I just said you replace this with 1 over n xi zi transpose. Also replace this with that. Also replace this with, say, 1 over zi transpose inverse. Okay, so if you need, you can just use that, or if you need this, you may use this. So estimation of the variance is simple, but you have to understand what is available and what is not. That's the point.